So with all these types of energy, I wanted to bring up the law of conservation of energy. And I love talking about this because it really is so relevant to how we get energy in our world, whether it's renewable energy or whether we're burning fossil fuels or whatever it is. So this idea of a law of conservation of energy, this is saying energy cannot be created nor can it be destroyed. Law of conservation of energy, this is where essentially it is saying that, and yeah, energy is being conserved. Okay, well, what does that really mean? All right. So essentially, if you've got one type of energy and you convert it into another, which happens all the time, and it's actually fairly easily done, then you're always going to have the same amount of energy you started with as you ended with. And so it can't just appear out of nowhere. So it all needs to be accounted for. Okay. So one example I like to use is a dam, a hydroelectric dam. And let's think about where the energy is starting out. All right, so let's think of a hydroelectric dam. I feel like I should use a different color, but I don't have blue. I want blue for, water. Okay, that's all right. We'll have green, aqua. All right, so we've got our dam. Okay, what is the dam doing? What is that dam doing? All right, we have water. And yeah, I don't have to write it as H2O because the main thing is we have these molecules of water that are flowing in a river, right? And then there is a dam that is stopping the water. So we have a water level here, and then the water below the dam is lower in energy. Okay? So within the mechanism of the dam, and I'm not even going to pretend that I know exactly what the structure of a dam is, but we do know that we've got water up here and down here. Okay, so that means that the water up here has greater potential energy than the water down here, and within the walls and the structure of the dam, etc., the water is dropping. Okay, so in terms of elevation, it is dropping. Okay, so we have potential energy, okay, that's getting converted. And we have these water molecules that are dropping down to a lower elevation. Okay, and so they are moving, right? They're moving up here and they're moving as they fall down. So we essentially have this conversion to kinetic energy. I'm not going to keep writing the word energy over and over. So kinetic, I don't even need to put E, because it's all energy. Anyway, so we've got this movement of the molecules, right? Well, they're also in my understanding of a dam anyway, is that there are these turbines, right? That are then getting moved. Let's see if it's pushing that way. Probably spins that way, right? Okay, something like that. So we have this movement of an object that is caused by the motion, the kinetic energy of these molecules. So here we have a conversion to mechanical energy. You could also say, oh, it's the kinetic energy of the water molecules then causing the turbines. I don't know what they're made out of, but probably metal, I guess. And those then are moving in this kind of kinetic way. Okay. So in any case, we've got this mechanical energy. All right. So these turbines are moving, and then once again, we have our clever engineers, which can then cause a turbine that is moving to, and there's usually some kind of solenoid in there or something, but you can get electrical energy out from that. And then it's like, yay, it goes into the grid. It is then distributed in that region, and then other people can get electrical energy out. Okay. Now, there is a little byproduct of all of this that I haven't mentioned, all right, and that is heat. And essentially, the role that heat energy plays in things like this, as it's being converted, energy is being converted from one type to another, is that this is not a 100% efficient conversion. Okay? There's always going to be a loss of heat. So let's see, how do I want to do this? Essentially, we also have heat coming out. The issue with heat is that in many cases, it's difficult to harness that energy. Okay, that's not always true. You can harness heat energy, but when it's not heat that you mean to capture, here we want to capture the kinetic energy. Then when heat is lost, it's just kind of seen as like, we lost some heat energy. No big deal. It's water, and the water's cooling it down, blah, blah, blah. Okay, but this does happen in every step of the way, that there is this loss of heat, this loss of heat, this loss of heat. Okay. And so this contributes to the inefficiency of the conversion, and it is just a nod to the law of conservation of energy, that your potential energy was converted into heat energy and kinetic energy. And so if you were to argue, hey, wait a minute, we lost energy because we did not get 100% conversion of our potential energy to our kinetic energy. And you can remedy that argument and say, no, conservation of energy was upheld because some of that energy was transferred or was converted into heat energy, and we were not able to capture that. It was lost into the universe. It manifested its way by increasing the temperature of, I don't know, the surroundings nearby, but it was not harnessed in a usable way by the hydroelectric dam people, right? So this is something that you see regularly. Things heat up, right? When you have your charger on your cell phone and you notice it heats up, right? Yeah, because there is this byproduct of heat that is happening when we have this conversion of electrical energy to chemical potential energy, when you're essentially charging up the battery inside there. Okay, so the battery is a chemical reaction, of redox reactions happening in there. So you're just recharging that. So another here's a little gloomy Halloween science thing, nerdy thing. Notice how heat is lost in each one of these steps, and that is true for nearly every conversion of one kind of energy to another. Okay, so now imagine that we're in a universe that is 6 billion years old. How old's the universe? Something, many billion years old. And you think about all the conversions of energy that happen, and I'm not even talking just on planet Earth, I'm talking everywhere in the universe, that there's all these things happening, and there's these collisions of asteroids, and there's supernova, and planets being formed, and whatever. And in all of these things that happen, heat is being lost in each one of these conversions. Okay? And so there is this very doomsday theory that eventually, with each kind of not chemical, because it doesn't have to be chemical, each time that there is a conversion of energy, if some of it is lost as heat, then eventually everything in the universe will just become heat. And it is known as the heat death of the universe. That the universe will just be this like blob of just heat. And I don't know, it's just like kind of creepy. So some physicists have said, no, it's not going to happen. But anyway, I find it fascinating when there's a scientific concept that is just kind of spooky and also dramatic in some way, where it's almost like it's brought in this theatrical element into the sciences. And I would say that is also true for something called the ultraviolet catastrophe, which was this observation in the early 1900s when scientists were looking at when they were heating up objects. And when they heated up an object, like just imagine an electrical stovetop, and you heat up an electrical stovetop and it begins to glow. And at first it's glowing a dim red, and then if you heat it way up, it glows a brighter orange, and even more, and it's a yellow. And if you heat it up enough, it could just be this bright white. Okay? Now, most stoves are not going to get so hot that they burn bright white, because they would probably burn people and possibly cause houses to burn down. It could be so hot. But if you've ever seen videos of heating up metal, so say it's I don't even know what do you call them, the people who make things out of metal, metallurgists. But I'm actually thinking of the blacksmiths. That's what I'm thinking. So when they heat up metals and they become white hot, then you have this white hot, and essentially if it's white, that means you have all the colors in the visible range, right? And so what people theorized is that as you heated up something more and more and more, it would then begin to glow in the ultraviolet region of the spectrum. Well, as it turns out, that was not observed. Lots of experiments done, and things they glowed even brighter white. They never started glowing in the ultraviolet region. And this actually was astounding to many of the physicists around the 1900s, in the early 1900s, late 1800s. And so this was astounding. It was disturbing. They were all kind of freaking out, basically. And they called it the ultraviolet catastrophe. And again, I just love that because it's just so like theatrical, and I don't know, I just love it when science gets all, brings some emotion into it. It's just kind of fun. So I put the heat death of the universe into that category as well.